Hi everybody. Today we're going to be working on Green's theorem. Now for Green's theorem, what we're going to do is we're going to analyze this curve that we're going to be given, and we then want to identify, does the curve have positive orientation? Meaning, as we traverse the curve, is it traversing in a clockwise orientation? Alright, my apologies, in a counterclockwise orientation. If it's counterclockwise, then it's a positive orientation. If it's a clockwise orientation, then that's going to be a negative orientation that we're going to be observing. Now, Green's theorem says this, that as long as we have a curve C that's positively oriented, that it's piecewise smooth, simple, and closed curve, and we're going to let D be the region enclosed by this curve. So if you look at the pictures here, we have some curve C that encloses this domain or this region D. So if P and Q have continuous first order partial derivatives on that region D, then we have that the line integral here can be expressed as the double integral over that region D for the partial derivative of Q with respect to X minus the partial derivative of P with respect to Y. And this is going to be with respect to that area because, again, it's encompassing that domain. Now, the different types of notations for Green's theorem are here that we use. We can use a little line integral here with a circle around it. We can do a line integral here with an orientation along that circle, or we can just denote here that we're looking at partial derivatives for that domain that we're going to be observing. So this notation would directly tie into this one here. So there are different notations that we use for Green's theorem, and again, we just have to make sure that whatever book we pick up or whatever forms we come across, we should always be observing that different notation that we can use for Green's theorem. Now, let's go ahead and let's look at this specific example. This example says that we want to use Green's theorem to evaluate this given line integral. The line integral is going to be over the curve for xy dx plus x squared y cubed dy. And C is going to be the curve that's given by the triangle with the given vertices of 0, 0, 1, 0, and 1, 2. And this curve is going to have positive orientation. Now, again, I want you to think about that positive orientation. And positive orientation for us just means we're going to go around counterclockwise. If you remember back when we were doing line integrals back in beginning chapter 16, the direction that we traverse a curve definitely matters if we're taking these integrals with respect to x or with respect to y. If we take the line integral with respect to the curve itself, then naturally the orientation will not matter because, again, the way we traverse a curve with respect to the actual parameters given will not matter. But in this particular case, since we are traversing the actual curve using these mixed line integrals, that dx dy, we specifically need that orientation to take place. So, looking at Green's theorem here, what I'm going to do really quickly is I'm going to start identifying from what I'm given. I'm going to identify that within this line integral that was given to me for xy dx plus x squared y cubed dy, I actually have my p and my q given to me. This here's p, and this term here is q. Now, why do we want this? Well, we want this so that we can start identifying. We need to start identifying partial derivatives in this particular case. So what I want to do now is I want to find some of these partial derivatives, that way I can keep working with them. So as you see the definition up here, I found p and I found q. So now in order to set this up using the double integrals, I'm going to go through and I'm going to start integrating over that region, that area D, but I'm going to integrate my integrand here, which is going to be my partial derivatives. So I'm going to need the partial of p with respect to y, that's going to be x, and I'm going to need the partial of q with respect to x. That's going to be 2x, oops, excuse me, and that one was y cubed, my apologies. Y cubed, there we are. So that's going to be 2x y cubed, nice. So when I set this double integral now, this double integral over my region D is now going to be my partial of q, which was 2xy cubed, minus just the x value, and this is going to be dA. Now, when I'm looking for that value, what I'm going to do is I'm going to start looking at this region D right in here, and that's the region that is encompassing, or that is being closed off by that curve. So let's go ahead and let's figure out, how do we want to do this? Do we want to take these vertical heights, or do we want to take these horizontal heights? In other words, these horizontal widths for this region. All right, because again, we have to do this double integral. Now, I typically like to do just vertical heights if I can. To me, that's more of an intuitive way to set up these integrals. And so what I'm doing here is I'm just going to set this up, and I'm going to do my dy's first. My heights are going to change first, vertical heights first, and then my x's are going to change. The x's are always going to change from 0 to 1, so that's not too bad. They change from 0 to 1. But then my y values, they do change. The y values, if you notice, they go from the bottom of this segment here, which is 0, and they go all the way to the top of that segment. And the top of that segment is this line, which means we got to figure out what that line is. What is that equation of the line? Well, we know the equation goes through the origin, so that's an intercept, y-intercept of 0, 0. And we know that it goes up 2 over 1, which means that's the slope, which means the line is y is equal to 2x. All right, so there's my line. Y is equal to 2x. Not bad. Which means my upper bound here for that innermost integral is going to be the height of that segment, which is just y is equal to 2x. And that's what we should get. Now from here we could just go through and finish off this double integral. This is going to be the integral from 0 to 1. And let's see here, we're integrating with respect to y first. So that's going to leave us with x, y to the 4th, divide by 4, so that's going to be 1/2 minus xy, and that's going to be evaluated from 0 to 2x dx, again from 0 to 1. And now I'm going to evaluate only my y values, because those are the ones that we integrated, so it's going to be 2x to the power of 4 minus x times 2x, and then the values of 0, they're just going to go away. Alright, this is going to be the integral from 0 to 1. This is now going to be 2 to the power of 4, but then divided by 2, so that's just 2 to the power of 3, so that's just going to be 8, and this is going to be 8x to the 5th minus 2x squared dx. And I believe you guys can take it from here. Alright, so what I want you to do is I want you to take it from here. You know what? Actually, no. I'm not going to have you guys take it from here, simply because I want to actually show you what we can do with this. Alright, so let's go ahead and let's finish this off. This is going to be 2/3. There we are. Alright, so awesome. So we were able to do this using Green's theorem. That's looking pretty good. All right, so look at that work there. Now, using Green's theorem is, once again, beneficial and nice. Let's see what would happen if we were to do this without using Green's theorem. So we're not going to use Green's theorem for the next part. All right, so I'm going to redo this question again, But this time around, we're not going to use Green's theorem, which means we're just going to use line integrals to traverse this curve. All right, so again, it's going to look almost identical to what we have. All right, so here's a question that we want to evaluate this line integral. All right, it's the same line integral that we were dealing with up here. All right, so same vertices, same orientation, everything's the exact same way. What we want to do now is we want to approach this using parametrization. So what we have here is we have these three different curves. We have curve number 1, we have curve number 2, and then we also have curve number 3. So curve C is made up of curve C1 union C2 union C3. So this means that we're going to have three different line integrals. So let's go through and let's start identifying, or let's start parametrizing what are the equations that we're going to need. Alright, so let's go with the first curve C1. So I'm going to go with curve C1. Curve C1, that has these x values that change. So if the x values are changing, I'm just going to assign that my t value. Y values, well, the y values are not changing at all. If they're not changing at all, that means they are 0. Now, what t values is this moving through? So this is going to be for the t values being between 0 and 1. Nice. So far what I did was I built this specific parametrization that I said this is going to be t and 0. And this only works for t being bounded between 0 and 1. I want to find the derivative. The derivative here is just going to be 1, 0, which means the magnitude of that derivative is just going to be 1. Alright, I'm going to keep that in my back pocket. Alright, we are going to need that. So curve number 2. So here goes curve 2. Alright, curve number 2. My x values are not changing, but the x values are staying constant at 1 for curve number 2, and that's this vertical line. So for that equation, what I'm going to do is I'm going to say that my x values are constant at the number 1. My y values are the values that are changing, and they're only changing between 0 and 2. So I'm going to just classify this as t, and this is going to be for my t values being bounded between 0 and 2. This then tells me that r of t, my parametrization for that vertical line, is just going to be 1 comma t. Now my derivative here, r prime, is just going to be 0, 1. Once again, we get a really nice magnitude to just be 1. Alright, everything's looking good so far. Let's go with the third curve. Curve number 3. So here goes curve number 3. Curve number 3. Now, if you remember curve number 3 had this equation y is equal to 2x. Which then means our x values are changing. So what I'm going to do here is I'm just going to say x is going to be t, which if x is t, then that makes y just 2t, right? Because of a nice substitution, if t is x, then this is just y is equal to 2x. Now, this works for certain t values. What are the t values that work? Well, let's start investigating those t values. Alright, so a t value, let's see, t is equal to 0. So what happens if t is equal to 0? If t is equal to 0, then we naturally get 0, 0. And let's say if t is equal to 1. what happens if t is equal to 1? Well, if t is equal to 1 here, this is just going to be 1, and that's going to be 2, which means we get this. Awesome. All right, looking good so far. Now, we got to be careful here. Be very, very careful here. I want you to analyze what type of orientation does curve number 3 have? So if my parameter goes from 0 to 1, right, because my parameter for t is increasing from 0 to 1, what are my points doing? At 0, they're both at 0, 0. They go to 1, that means they're moving in a clockwise direction as they're increasing, which is a problem for us because we cannot have them move in a clockwise direction. This is moving counterintuitively. So we now have to think of a way to kind of counteract that, because the way we parameterized it in this particular direction, it's going the wrong direction. So we need to counteract it. Either we did something wrong, or we just need to think about it slightly different. All right, so let's start analyzing that. All right, so here we go. Now, we could go through a different parameterization, all right, which, you know, if you want to go with that, by all means, that's going to be perfectly fine. But if you want to recall, we have one of these statements here that says that if you take a curve and you traverse it negatively for some pdx plus q dy, then what you get is a negative integral over the curve that you're integrating for pdx plus q dy. And this is what I actually want to use, because I'm traversing the curve negatively. I can still get that evaluation if I think about the whole integral just being negative. So I want to just hold that in my back pocket and say, you know what, I don't want to go for the reparametrization. I know that this curve is traversing negatively, so what I'm just going to do is I'm going to slap a negative on that integral, and that way it will get me the answer that I need. All right, so I'm just going to put a slight note here. I'm going to say note the parametrization Let's actually clean this up a little bit better. I don't like the way this is looking. So this parametrization, the one that we chose here, is traversing in a negative direction, or opposite direction, so we're going to need to account for that. All right, now in my accounting, I'm not going to do it just yet, but I will go ahead and I will write all this out. So my parametrization here is t and 2t. My derivative here is just going to be 1, 2. The magnitude of this is going to be root 5. There we are. Perfect. So now as we start going through, as we start figuring out what is this integral that I'm looking at, so I want to traverse this integral for this given curve, which was this xy dx plus x squared y cubed dy. This is now going to be split into 3 different curves. So it's going to be along curve number 1, xy dx plus x squared y cubed dy, plus along curve number 2, plus along curve number 3. like such. And now all I have to do then is go through all of my different parameterizations and start making my substitutions. Once I'm able to do that, then I will be able to go ahead and solve for this specific integral. Alright, so here we go. Equals. Alright, curve number 1. Here goes curve number 1. So curve number 1, I believe I did that in green, so I'm going to go switch over to green. All of my x values were now classified as just t values. X was equal to t on that parameterization. If you want, you can just revisit that here. X was equal to t, y was equal to 0. So y was equal to 0. Alright, I need my dx. My dx, that's going to be this piece right here. So dx, that's just 1 dt. That's 1 dt plus x squared. And again, my x value was just t. Y value was your 0, so that's 0 cubed. And then dy, well, what was dy in this particular case? Dy, that's just 0, so this is going to be 0 dt. Alright, that was my first integral. Those t values were bounded between 0 and 1. So my integral goes between 0 and 1. Plus the next integral. So the next integral, curve number 2. So for curve number 2, let's go over to my bounds really quick. My bounds on curve number 2, they went from 0 to 2. So I'm going to go from 0 to 2. My x values were 1, or was 1. So my x value is 1. My y value is just t. So this is just x times y, so 1 times t. I need my dx. My dx was actually 0, so that's going to be 0 dt plus, and that's going to be this next term here. So the next term, x, well, that x was my 1, so that's going to be x squared. There we are. Y, my y values here was just t, and that y is going to be cubed. Alright, and now I need my dy. So my dy should just be 1, so that's going to be 1 dt. Nice. Now I'm going to pause here really quick because I just realized I kind of made a little fudgeums right over here on the first equation. X squared y cubed, this is supposed to be x squared y cubed. There we are. Alright, awesome. Now let's keep going to the very last curve. The very last curve, here we are. This is going to be the integral, and let's see, my t values were going between 0 and 1, so I'm going to go between 0 and 1. Now remember, my curve was traversing negatively because of that negative orientation. So what I'm going to do is I'm going to make this integral negative, and I'm going to make it negative because, again, I'm traversing this curve by the way I parameterized it negatively. So the integral from 0 to 1, here goes. I'm going to have my x cubed, sorry, my x and my y. So x was t, so I'm just going to have t multiplied by 2t. dt, well, that's just going to be, or sorry, dx, that's just going to be 1 dt. Plus, I'm going to have my x squared. So x was t, so that's just going to be t squared. My y values are 2t, so that's going to be 2t, and that's going to be t cubed. Now I need my dy's. Dy's, that's just 2, so that's going to be 2 dt. And there you have it. So here's the line integral that, or the line integrals that we need to go through and we need to evaluate. All right. Now there are going to be some really nice simplifications here because anything that has a 0 is going to get canceled out automatically. So look at my first integral here. So t times 0, well, that's going to be 0, so that kind of goes away. All right, so that's just 0. t squared times 0 cubed times 0 dt, that goes to 0, which means my first integral is just a big bunch of zeros. Alright, that's not too bad. Second line integral, this first term here on the second line integral has a 0, so that's going to be 0 dt, so this part is just going to go to 0, and I believe that's all that cancels out. So let's keep going. My first integral, again, got turned to 0, so I'm going to completely omit that integral. Okay, so the first integral produces a 0. All right, there we go. Second integral is going to go from 0 to 2. The first term is 0, which means all we're doing is we're integrating t cubed dt. That's again for that second integral. All right, second integral, second term, that's all we're integrating, minus dt minus the integral from 0 to 1, and this is going to be, let's see, that's going to be 2t squared, so 2t squared, and then this is going to be t squared times t cubed, so that's going to be t to the 5th, and then we have a 2 cubed, so that's going to be plus 8 t to the 5th, making sure, oh, there was an extra 2 that I forgot to account for. 2 cubed, that's 8, times another 2, that's 16. There we are, so 16 t to the 5th, and that looks good, and this is all dt. There we are. Alright, it's looking good, it's not too bad. So let's go through. That's going to be here 1/4 t to the power of 4, evaluated from 0 to 2, minus, this is now going to be 2 divided by 3 t to the 3rd, plus, and let me see, that's going to be 16 divided by 6, I believe, so 16 divided by 6, that should be 8/3. Alright, 16 divided by 6, 8/3, that's going to be t to the power of 6, and that's going to be evaluated from 0 to 1. Alright, let's keep going. So this is going to be 1/4 multiplied by 2 to the power of 4 minus 1/4 times 0 to the 4th minus, here we're going to have 2/3 times 1 cubed plus 8/3 times 1 to the 6 minus 2/3 times 0 cubed minus 8/3 times 0 to the 6. Alright, so now we can go through and we can start making our insertions here. So 2 to the power of 4, that should get me 16. 16 divided by 4 should just get me 4. Nice, and then that part's going to be 0, so that goes away. And then here we're going to be left with minus 2/3, so that's minus 2/3, got it. And then plus 8/3. So plus 8/3, just like this. Alright, it's looking good. That's going to be 4 plus, and that's going to be 6/3. Something like this. Alright, looking pretty good so far. Which, in this case, should get me 2. And we ran into a slight snag. Alright, and here we are. So again, I said slight snag. You're absolutely right, man. My arithmetic is horrendous. I double checked this whole problem, and it turns out my arithmetic, I completely forgot to distribute this negative right in here. Oh my goodness. So there you have it. Just by forgetting to distribute that negative here definitely changes the whole problem, because now 4 minus 2/3 minus 8/3 should give me 2/3. Now 2/3, is this the exact same answer that we got last time? It sure is. So what I want you to do is I want you to then look at this amount of work that needs to be done with these two problems. Number one, that problem was just using Green's theorem, using a double integral. Bam, we were done in like 5 different steps. If we didn't use Green's theorem and instead of we parameterized using curve arguments, well then that takes a really long time and a deeper understanding. So Green's theorem is here to help us to do these calculations, which is going to be very, very beneficial for us. All right, so please be very mindful of this. On your final exam, you will have to do both methods. One's going to be with Green's theorem, and again, Green's theorem just uses those double integrals, and one is going to be just with the evaluation of line integrals along those curves. So again, be very, very mindful of that. All right, now we're going to move on to a different question. So here goes the next question. We want to evaluate this line integral over the curve, and we're going to do this for y cubed dx minus x cubed dy, where the curve C is a positively oriented circle of radius 2, centered at the origin. All right, nice. So what I'm going to do really quickly is I'm going to get a grid going. That way I can try to draw this domain or this region that I'm going to be integrating over. Alright, so here's my grid, and they're telling me that I want some curve that's going to be positively oriented around the circle of radius 2. So there goes my circle. Alright, there we go, slightly better. So here's my curve C, and my curve C is encompassing, or it's enclosing, this area, and I'm going to label this area D. Alright, that's going to be the area that it's going to be enclosing. So when I want to set up this line integral, or when I want to solve this line integral for the line integral being along the curve, that's going to be y cubed dx minus x cubed dy. Instead of doing the parametrization along the curve, what I'm going to do is I'm going to look at the double integral over that region. So what I'm going to do really quickly is I'm going to identify what's my p and what's my q, and then I'm going to go from there. Alright, looking at this here's my p value, and this here is going to be my q value, which then tells me that p is going to be y cubed and q is going to be x cubed. Sorry, negative x cubed here. Negative x cubed, there we are. Perfect. So now when we go through it, we're going to take the partial derivative of p with respect to y. This should give me 3y squared. Partial derivative of q with respect to x, this should give me negative 3x squared. So my double integral then in this particular case is just going to be the partial of q with respect to x, which is negative 3x squared, minus the partial of p with respect to y, which is 3y squared. And then this is going to be over the domain with respect to dA. Now let's go through and let's start setting this up. Well, what kind of domain we have? If we have a circular domain, which chances are I want to use polar coordinates. So if I'm using polar coordinates, I then need to identify what radii am I sweeping through. At all times, the radii that we are sweeping through, or that we are elongating to, is going to be the radii fitting from 0 to 2. Now, what angle measurements are we traversing through? So the angle measurements, they start at the positive x-axis and they move around in a counterclockwise direction, which means we go from 0 to 2 pi. And again, we're moving positively oriented. positive orientation would mean that we're moving in this particular direction, like such. All right, so we just got to be very careful with that. All right, now here I'm going to factor out a -3. So if I factor out a -3, I'm left with x squared plus y squared. So what's x squared plus y squared? That's just r squared. And when we change our variables, we go into r dr d theta. R dr d theta, according to our change of base process. Which now just means I need to evaluate this double integral here. So the double integral is going to be -3 multiplied by the integral from 0 to 2 pi, integral from 0 to 2, and that's going to be for r cubed dr d theta. So go through and evaluate this particular integral, and it should be quite nice. So take some time, put pause on the video, and evaluate it. You should get something along the lines of -24 pi. Awesome. Awesome so far. So these are the types of problems that definitely help us out when we're looking at Green's theorem and how we want to, again, use and implement Green's theorem. Alright, so let's start now looking to generalize Green's theorem a little bit more. Alright, so I'm going to be working on generalizing Green's theorem a little bit more, and what I want to do is I just want to create this one boundary here for this given curve. Alright, so here I'm going to have curve C, and curve C is going to be traversed, or I'm going to attach a positive orientation to curve C, like such. And what I want to do here is I want to start looking at curve C. That curve C is encompassing, or it's enclosing a certain region, and we're going to call that region D. And what I want to do now at this particular time is I kind of want to cut this. I kind of want to say, okay, well, I'm traversing this trail here in a positive orientation, but as I get through halfway, I figured out, hey, I'm kind of tired and I kind of want to go back. All right, how do I then go back without finishing this whole curve? Well, what we can do is we can cut the curve. Let's say we cut the curve here, as such. Now, cutting this curve, this now gives us a new path. Alright, so this gives us a new path. Now, the new path that this is going to give us, I'm going to outline with these green arrows. It's going to be moving in this direction, and then it's going to move down in this direction, and then it's going to come back this way, and this way. But it also gives us a different path, and I'm going to outline this in green, sorry, in orange, which moves in this direction, as such. So now we have these different curves that we then start looking at. So what I'm going to do is I'm going to then start defining this. Alright, I want to make sure that we define this a little bit more clearly, that way we can extract what it is that we're looking at. So this curve out here, this orange piece that lies on the original curve, I'm going to call that C2. I'm going to call this outer piece over here on the right, I'm going to call that C1. And I'm going to call this curve right in here that traverses both directions, I'm going to call this C3, and I'm also going to call it negative C3. And why is that? Well, because one way it takes a positive direction, the other way counteracts that direction. So we have these two different curves that we then start looking, or sorry, these three different curves that we then start looking at. Naturally, this then subdivides our domain, or our region D, into two different regions. This now subdivides the left region into D2 and the right region into D1. So I'm going to start listing what I have over here. I'm going to say the boundary D, the boundary of D1 is C1 union C3. The boundary of D2 is C2 union, that was C2 union with this negative traversing of curve 3. Altogether, curve C is made up of curve 1 union curve 3 union curve 2 union negative curve 3. Now, if you follow the unions along, then the negative traversing with that positive traversing of curve 3, we're only going to get C1 union C2, which again naturally makes just that outer portion of the curve. So the big question is, why am I looking at this, and why do I want to look at this so abstractly? Well, one of the items that I want to work with in this particular case is now that I want to analyze what is the double integral over the region that I'm looking at, domain D, that's going to be this domain D here, for this particular case, partial of Q with respect to X minus partial of P with respect to Y dA. Well, in order to answer this question, D, in this particular case, our main domain, we know, or we can see here, that D is just made up of two smaller domains, or two smaller regions. Well, how do we work with that? We say this is the double integral of domain 1 union domain 2, and that's going to be for Q partial of X, Q partial of X minus P partial of Y dA. But then this is just the double integral over the first region, like such, plus the double integral over region 2 for Qx minus P sub Y dA. There we are. Now, looking at these double integrals, well, these double integrals, this now satisfies Green's theorem for that double integral, at least for region D1 and region D2, which then means that we can then start analyzing these specific line integrals for D1. Now, D1, domain 1, or that region 1 is closed off by these two curves. It's closed off by C1 and C3. So the line integral should be C1 union C3. And that's going to be for P dx plus Q dy, plus this second line integral for region D2 is closed off by curve C2 union negative C3. And that's going to be once again for P dx plus Q dy. Now I want you to start to see what's going to happen here. Well, what's going to happen here in this particular case is that we're going to have this line integral. Since this line integral traverses two different curves, we can then split the line integral into those two curves, plus the line integral for C3 for P dx plus Q dy, plus the line integral for C2 for P dx plus Q dy. All right, looking good. Plus the line integral for negative C3, and that's going to be for P dx plus Q dy. Now, check out what happens here. Well, what do we know about these two integrals here and here? We should know that those two integrals are negatives of one another. In other words, they're opposites, meaning that they're opposites, they're going to cancel each other out. So if that's the case, then aren't we just left with C1, which is just for P dx plus Q dy, plus the integral for C2, which is just P dx plus Q dy. But isn't this just the line integral for C1 union C2? And this is for p dx plus q dy. But isn't this C1 and C2? We said that C1 union C2 is just the original curve. So isn't this just the original curve for that line integral for p dx plus q dy? Now, this is a very, very long process to establish here that even if we insert a path, and we split and we subdivide our initial region into smaller subregions, we can still just go through and evaluate the curve on the outermost region. That curve on the outermost region is still going to give us that Green's theorem result. So it doesn't matter how many times we then subdivide this initial region. This work now shows that we can keep on subdividing how many ever times we want, and we're still going to get the desired result by integrating on the outer curve. And that's what this result says, which again is very, very beneficial for what we have to do. All right, awesome. It's looking good so far. Now, what if now some of these regions, look at your regions D1 and D2. What if we had a hole on one of those regions? Well, that adds a wrinkle to our story. All right. So what I'm going to do here is I'm going to give you this depiction here. All right. We're going to have this annulus. Annulus is a flat donut that we look at. And it has this specific orientation. All right, so this is going to be a curve. Let's call this curve C, and curve C is going to be made up of C1 and C2. All right, so here I have C is C1 union C2. The domain or the region that I want to focus on in here is going to be the inside of the first circle. Sorry, inside of the second circle, but outside of the first. All right, so this is my region that I'm looking at, D. Perfect. So notice curve number 1 has positive orientation, curve number 2 does not. All right. So what I want to then do is I want to then start analyzing this specific annulus and how this is going to play out for Green's theorem. In what way is it going to play out for Green's theorem? All right, so here we are. So what I'm going to do here is I want to make sure that all of my boundaries here on this curve, on this annulus, are encompassing my domain. So in order for me to do this, what I'm going to do is I'm going to start subdividing now. All right, so I'm going to insert a different curve. The curve that I'm going to insert here is going to cut through there, and it's also going to cut through here. All right, so far I have curve 1 and I have curve 2. All right, that's pretty good. I'm actually going to restructure those, and I'm going to restructure this guy here as well. All right, perfect. Now I'm going to start labeling my curves. That way I can have a definite way to reference these. So here we are. I'm going to have curve number 1. So curve number 1 is going to be right out here. That's going to be the top part of that annulus. Curve number 2 is going to be the curve right inside of here. Curve number 3 is going to be this curve right down here. Curve number 4 is going to be the curve on the outside of the annulus, that bottom part. So that's curve number 4. All right, curve number 5 is going to come over here. So curve number 5 is going to be moving in this direction. Negative curve 5 moves in the opposite direction. All right, I have curve number 6. That's going to move in the direction to the right. Curve negative C6 is going to move in the direction to the left. So now as we start traversing on this annulus, we can start traversing. If you follow my mouse here, I'm traversing along the top curve. I get to this red part here and I cross into the curve. I go back out this way. I'm going on the inside of this arc, come down to this red part, and then I traverse outside of that annulus, and I keep doing it over again. That's only for the top part. I can do the same thing for the bottom part. Now, what I want to look at is I want to start looking at these boundaries. So I'm going to look at the boundary for D1. The boundary for D1, this is going to be curve 1, union, curve 2, union, curve 5, union, curve 6. So D1 naturally just becomes this upper domain, or that upper region. Now I want the boundary for D2. Well, the boundary for D2, that's just going to be C3, union, C4, union, negative C5, union, negative C6. And again, that's going to be this region right down here. It's going to be the bottom part of that region for that annulus. Now, once again, we want to start investigating this, and we want to start investigating this using Green's theorem. So I'm going to say here, a curve was equal to C1 union C2. There we go. All right, so I'm going to start looking at this double integral. So this is the double integral over my initial region here, D, and that was going to be for Q partial of x minus P partial of y dA. Well, this initial domain now gets split into two different domains. So my initial domain D now got split into two different ones because we inserted this new section. So this is going to be D1, which is still going to be Q partial of x, P partial of y, and this is going to be dA. And I'm going to add this to the double integral over domain 2 in order for us to find that region. And that's going to be for Q partial of x minus P partial of y dA. But now if you look at the boundaries that we listed right up here for those two curves, or for those two regions, that's now going to give us, well, for the first one, for the first domain here, that's going to give us the integral, line integral, for C1 union C2 union C5 union C6. And that's going to be for P dx plus Q dy. Plus, that's going to give us the second integral here, the second double integral. So the second double integral over the curve for domain 2, that's going to be for C3 union, I don't like the way that came out, C3 union C4 union negative C5 union negative C6. And that's going to be for P dx plus Q dy. Alright, it's looking good so far. And what we're going to do is we're going to do the exact same thing that we did last time. We're going to start expanding this. So if we start expanding this line integral, we get C1 for P dx plus Q dy. Then we get plus, I meant to say positive and it came out as pos. P dx plus Q dy plus the integral for c to the 5th P dx plus Q dy plus line integral for C6, that's going to be P dx plus Q dy plus, and we're going to keep going. We're going to keep going till we get to the line integral for this very last one for negative C6, and that's going to be for P dx Q dy. And what you're going to notice is that these C6 integrals are going to cancel because they're opposites of one another. Not only are they going to cancel, C5s are going to cancel as well. which means we get a lot of cancellation happening, and at the end of the day, this just turns into a line integral that uses curve 1, curve 2, curve 3, and curve 4. In other words, the ones that did not cancel out. Now, why is this beneficial? Well, I want you to then look at what does curve 1 union curve 2 union curve 3 talk about. Curve 1 union curve 2 union curve 3, that's curve 1, curve 2, curve 3, and curve 4. That's just the original curves, C1 and C2. Now, what does that then tell us? What does that then split this into? Well, that just now tells us that this is really just the line integral over the main curve for p dx plus q dy. Now, I want you to then think about that. As long as we're just looking at the region right in here, there's no need to go through and cut to find out what is this initial curve right inside doing. We can just make sure that if we want to find the line integral for the curve that is encompassing this region, all we have to do is go back and interpret what is the original region that we are looking at. So there's no need to subdivide. Even if there's a hole, there's no need to subdivide. Subdividing, it is beneficial, but it's going to be the long way around. So let's see. Can we then evaluate this line integral for y cubed dx minus x cubed dy, where the curve C are two circles of radius 2 and radius 1, centered at the origin with positive orientation. Alright, so let's go through and let's start looking at this. Now, what I'm going to do really quickly is I'm going to get a grid going here because, again, I want to look at what is this specific domain, what is the region that I am trying to answer the question for. Alright, here we go. So we had two different circles, one of radius 2 so there's radius 2 and one of radius 1. There we are. And so the region that's being encompassed here, or being enclosed, is this region right in there. So in order for us to set this integral, this line integral, so I want this line integral over the curve for y cubed dx minus x cubed dy, then what I need to do is I need to once again analyze what is my p and what is my q, and then take it from there. So looking at this here, I'm able to identify that p is just y cubed, q is just going to be negative x cubed, which then means that the partial of p with respect to y, that's going to be 3y squared. Partial of q with respect to x is going to be negative 3x squared. So my double integral over this region that I'm encompassing is going to be my negative 3x squared minus 3y squared dA. Negative 3 can factor. So negative 3 can factor. Now I want to set up my double integral here. So my double integral over that region, let's see, I need to find radii. So let's talk about the radii. What radii does that region extend through? Well, at all times the radii is just going from 1 to 2. Nice. Well, what about theta? What are the theta values traversing through? 0 to 2 pi. Nice. Alright, and then we factored out negative 3, so we're just left with x squared y squared, which just means that we're left with r squared. And then since we changed our variables, this is just r dr d theta. Nice. So what we did here is we just evaluated this, or we set up the integral so that we can start evaluating this particular question. Now, what I want you to do is I want you to finish evaluating this. This should be a very similar answer to what we got last time. The answer here is going to be 45 pi divided by 2. So negative 45 pi divided by 2. Now, again, I want you to then analyze, did we ever break up the region, even though the region has a hole in it? Right? No, we didn't. There's no need for that. All right. Awesome. So, everything's looking good so far. All right, we're able to extract using Green's theorem, and we're able to then subdivide using Green's theorem. So, that's now going to wrap it up for this particular section, and we're going to be moving on to the next section shortly. So I hope you all enjoyed the video, and stay safe. Have a good day.